on December the 19th, 2025, and at this precise moment, as these words are being recorded, as you're watching this coverage unfold, a visitor from the deepest reaches of interstellar space, 3I Atlas passing Earth right now. One question arises like, is it just a changed course? But data says the 3I Atlas is executing its closest approach to Earth, passing at a distance of approximately 1.88 astronomical units, which translates to roughly 281 million kilometers from where you're sitting right now, from the device you're holding, from the planet you call home. This is not routine celestial mechanics. This is not just another rock-tracing predictable ellipse through the gravitational architecture of our solar system. This is the third confirmed interstellar object in all of recorded human history to penetrate our system's boundaries, following the enigmatic Oumuamua in 2017 and the more conventionally cometary 2I Borisov in 2019. But the object we are tracking tonight, catalogued as 3I Atlas, is exhibiting behaviours that neither of its predecessors displayed, behaviours that are forcing real-time reassessment of fundamental assumptions about what travels through the space between stars and what purposes or origins such travellers might embody. Before we examine the extraordinary data streaming in from observatories worldwide, data that is literally arriving minute by minute as this recording proceeds, if you want to remain informed as this situation develops throughout the night, as NASA and ESA and independent facilities continue releasing observations and analyses that could fundamentally alter our cosmic perspective, you must subscribe to this channel immediately and enable all notifications. We are tracking this live. Updates will post as information becomes available. The story is unfolding in real time and you need to be here as it happens, not learning about it days later through filtered mainstream coverage that may not convey the full implications of what we are witnessing. Hit subscribe, turn on notifications, because the data we are about to examine suggests that 3I Atlas represents either the most bizarre natural comet ever observed or something that challenges our categories entirely. Let us begin with the visual observations, with what telescopes are actually seeing when they point at this visitor, because the appearance of 3I Atlas has undergone transformations over recent days that contradict standard cometary physics and that demand explanations we are struggling to provide within conventional frameworks. Just 48 hours ago, when the object was still approaching closest passage, when observatories were ramping up observation cadence in preparation for today's optimal viewing window, 3I Atlas appeared as faint magnitude 18 source on CCD sensors, barely detectable above background noise, requiring careful image processing and stacking of multiple exposures to extract signal from the chaos of photon statistics. We anticipated standard cometary progression, the well-documented pattern where objects brighten as they approach the sun due to increased solar heating, driving higher sublimation rates, followed by predictable fading as they recede and as volatile reservoirs in near-surface layers become depleted. This brightening and fading follows power laws related to solar distance, with brightness scaling roughly as inverse square or inverse cube of heliocentric distance depending on whether you're dominated by reflected sunlight or by intrinsic emission from excited gas molecules. Decades of comet observations have established these relationships with high confidence. We know how comets should behave. 3I Atlas did not follow the script. Instead of gradual monotonic brightening, the object's luminosity spiked, jumping several magnitudes in matter of hours rather than days, creating sharp discontinuity in the light curve that observers initially suspected might be instrumental artifact or data processing error. But independent facilities confirmed the spike. This was real phenomenon, actual change in the object's brightness that occurred far more rapidly than thermal models predict for ice sublimation, responding to increasing solar flux. Rapid brightness changes are not unprecedented in cometary science. Outbursts occur when subsurface pressure from trapped volatiles exceeds the structural strength of overlying material, causing sudden fracturing that exposes fresh ice to solar radiation and creates temporary surge in gas production. Comet Holmes in 2007 underwent extraordinary outbursts that increased its brightness by factor of nearly 1 million in less than 24 hours, transforming it from faint telescopic object to naked eye visibility. So outbursts happen. They are natural phenomena driven by the complex interplay between thermal gradients, structural properties, and volatile physics in heterogeneous icy bodies. But what distinguishes the 3I Atlas brightness spike from typical outbursts is not just the timing, but the colour evolution that accompanied it. And this is where observations transition from merely unusual to profoundly mysterious, where we move beyond the range of behaviours documented in our solar system's native comet population and into territory that demands new physics or new interpretations. As 3I Atlas crossed what astronomers call the frost line, the region of the solar system where temperatures drop below the freezing point of water and where volatile ices can exist in stable form on object surfaces, the spectrum of emitted light displayed distinct vibrant blue coloration. This blue emission is well understood in cometary physics. It arises primarily from carbon monoxide molecules and ionized nitrogen compounds that fluoresce under solar ultraviolet radiation, absorbing UV photons and re-emitting visible light at wavelengths, concentrated in the blue portion of the spectrum. We observe blue emission from numerous comets, particularly those rich in carbon monoxide ice, which sublimates at temperatures far below water ice, and which produces characteristic molecular bands in spectroscopic observations. So the initial blue phase fit expectations. It indicated that 3I Atlas contained significant carbon monoxide, which is not surprising for an object that has spent millions of years in the deep freeze of interstellar space, where temperatures hover just a few degrees above absolute zero and where even super volatile species like CO remain frozen. The blue told us the object was activating, that solar heating was reaching levels sufficient to mobilize these ultra-volatile ices, that we were witnessing the awakening of a visitor that had been dormant throughout its long journey between stars. But then, as the object continued its approach, as solar distance decreased and heating intensified, the spectrum shifted. The blue coloration gave way to piercing green, the colour that has become iconic in popular culture as the signature of active comets, immortalised in photographs showing emerald-hued comas surrounding bright central condensations. Green cometary emission is also well characterised. It originates primarily from diatomic carbon, C2 molecules, and from cyanogen radicals, CN, both of which are produced when more complex organic molecules are broken apart by solar UV photons through a process called photodissociation. The parent molecules, likely to be more complex hydrocarbons or nitrogen-bearing organics, exist in the nucleus ice. When they sublimate and enter the coma, when they are exposed to the intense UV flux close to the sun, photons strike them with enough energy to break chemical bonds, fragmenting large molecules into smaller radicals that are excited into high-energy quantum states. These excited radicals then relax back to ground state by emitting photons, and for C2 and CN, the emission wavelengths cluster in the green part of the spectrum, creating the characteristic glow we associate with active comets. If the spectral evolution had ended there, if 3I Atlas had transitioned from blue to green and then maintained that green emission as it approached closest passage, we would classify as chemically rich but ultimately natural body. Interesting for the abundance of organic compounds it apparently carries, but explicable within standard framework of cometary composition, shaped by formation conditions in its origin, stellar system. But the story absolutely does not end there. The observations from the past 6 hours, the most recent data as this recording begins, reveal something unprecedented, something that has no clear analogue in the catalogue of cometary observations accumulated over centuries of astronomical study. The green emission is being overtaken by metallic golden tint, a warm yellowish gold coloration that makes the object appear less like dirty snowball, sublimating under solar heating, and more like polished metal, reflecting sunlight with high efficiency. This contradicts everything we thought we understood about cometary coma composition, and about how ice and dust mixtures scatter and emit light. There are extraordinarily few natural processes that can create sustained golden reflection in cometary environment, and those that do exist require very specific and quite rare chemical compositions or physical conditions. Sodium tails can produce yellow-orange coloration when neutral sodium atoms are ionized by solar UV and then emit characteristic yellow doublet spectral lines at 589 nanometers. This is familiar from laboratory flame tests, where sodium salts produce the bright yellow colour used in street lamps and fireworks. But sodium tail emission, while yellow, is distinctly different from what spectroscopic analysis is showing for 3I Atlas. The wavelength distribution does not match pure sodium emission. The spectrum shows broader continuous component, more like reflected sunlight than like discrete atomic emission lines. It looks, And this is the unsettling phrase that keeps appearing in observational reports. It looks almost solid. It looks like light reflecting off metallic surface rather than scattering off cloud of gas and dust particles. The albedo, the fraction of incident sunlight that is reflected rather than absorbed, appears to have skyrocketed to approximately 80% based on brightness measurements compared to solar distance. This is extraordinarily high reflectivity, rivaling some of the most reflective objects in the solar system. For context, fresh snow on Earth reflects about 80 to 90% of visible light, which is why snowy landscapes appear blindingly bright on sunny days, and why you can get sunburned from reflected sunlight even when the sun is at moderate elevation. Enceladus, the small moon of Saturn famous for its spectacular ice geysers erupting from South Polar region, has surface albedo exceeding 90%, making it one of the most reflective bodies we know, so bright that looking at it through telescope with sun behind you is almost like looking at white painted surface under floodlight. 3i Atlas is now displaying albedo comparable to fresh snow or to Enceladus ice, despite being at 1.88 AU from the sun where temperatures are far above the freezing point of water, where ice should be sublimating, violently creating thick, dusty coma that reduces reflectivity. Water ice exposed to sunlight at these temperatures does not remain pristine and highly reflective. It darkens as sublimation concentrates non-volatile impurities on the surface. It gets coated with dust. It develops rough texture that scatters light diffusely rather than reflecting it specularly like mirror. Yet here we have object that is hot, that is currently experiencing full intensity of solar radiation at distance, where Earth-like temperatures would prevail if we neglect greenhouse effects, and that object is reflecting 80% of incident, light with spectrum that suggests metallic or at minimum extraordinarily smooth high albedo surface. The standard model is breaking. We are seeing behavior that ice should not produce, that dirty ice definitely should not produce, that requires either novel composition or novel structure that we have not previously encountered in natural solar system bodies. And this brings us to what may be the most critical observation from the high-energy domain, to data that operates completely outside the visible light spectrum where human eyes and standard optical telescopes function, to measurements that probe the interactions between 3i Atlas and the solar wind environment through which it is moving. While optical telescopes were documenting the extraordinary colour transformations, while observers were scrambling to understand how blue could become green, could become gold, through any plausible sequence of chemical or physical processes, the Hubble Space Telescope and the Chandra X-ray Observatory were examining the object at the high-frequency end of the electromagnetic spectrum, in the X-ray regime where photon energies measure in thousands of electron volts, and where emission mechanisms are fundamentally different from visible light fluorescence. Comets do emit X-rays. This phenomenon was discovered somewhat surprisingly in the 1990s, when the Rosat X-ray satellite detected unexpected X-ray emission from several comets. The mechanism responsible is now well understood and is called charge exchange. Solar wind consists of high-speed stream of charged particles, primarily protons and electrons, but also heavier ions like carbon, nitrogen and oxygen in various ionization states, ejected from the sun's corona and accelerated to velocities of several hundred kilometers per second as they flow outward through the solar system. When this ionized wind encounters the neutral gas coma surrounding an active comet nucleus, when high-speed ions collide with slow-moving neutral molecules like water or carbon dioxide, charge exchange reactions occur where electrons transfer from the neutral species to the high-charge ions. These newly captured electrons are typically deposited into highly excited quantum states, far from the ground state, and they rapidly cascade down through intermediate energy levels by emitting photons. Many of these transitions occur in the X-ray portion of the spectrum, producing the characteristic soft X-ray glow that has now been detected from dozens of comets. The X-ray emission from charge exchange is diffuse, spread throughout the extended coma, and it varies smoothly as the density and composition of the coma fluctuate with changing outgassing rates and with the chaotic turbulence of the solar wind that creates regions of higher and lower ion flux. We expected to see this standard diffuse soft X-ray glow from 3i Atlas as solar wind ions interacted with its gas envelope. What we are actually observing is radically different from this baseline expectation and is forcing complete rethinking of what is creating the emission. The X-rays are pulsing. They are not exhibiting the random fluctuations you get from turbulent processes or from stochastic variations in solar wind density. They show sharp, rhythmic peaks, periodic enhancement and suppression of X-ray flux, occurring with structured temporal pattern that looks nothing like the chaotic signatures we associate with natural astrophysical processes operating in turbulent gas flows. This is the crucial detail that transforms curious observation into profound mystery. The X-ray emissions have structure, they have pattern, they repeat with regularity that implies underlying periodic driver rather than random environmental fluctuations. A NASA astronomer commenting on this observation in a report that was updated within the past hour, that is being written and revised in real time as new data arrives, noted cautiously that this emission pattern could potentially result from complex interactions between structured solar wind features and the comet's coma, but acknowledged that the amplitude of the signal, the sheer strength of the X-ray peaks, suggests processes that are more exotic than standard charge exchange physics can easily explain. When scientists use the word exotic in formal reports, it is diplomatic code for "we don't know what this is yet," for "this is outside the range of phenomena we have satisfactory theories to describe." The amplitude problem is this: charge exchange X-ray emission scales with the product of solar wind ion density and neutral gas density. If the coma is thick, if there is abundant neutral gas for the solar wind to collide with, you get strong X-ray emission. But spectroscopic and imaging observations indicate that the coma of 3I Atlas is relatively thin compared to many active comets at similar solar distances. The gas production rate inferred from optical emission is modest, so with thin coma, with limited neutral gas density, charge exchange should produce weak X-ray emission. But what we observe is exactly the opposite. The gas is thin, the neutral density is low, and yet the X-rays are blindingly intense by cometry standards, far exceeding the flux that thin gas interacting with solar wind should be capable of generating. This amplitude mismatch implies that the interaction surface, the structure that solar wind is encountering and responding to, might not be diffuse gas cloud at all. It might be something substantially different, something solid, something with properties that allow for much more efficient X-ray generation than gas interactions provide. If you have conductive surface, if you have material that can support currents and magnetic fields, if you have structure rather than just cloud, then interactions with magnetized solar wind can create very different phenomenology than simple charge exchange produces. Imagine metallic body rotating through the magnetized solar, wind plasma. The relative motion creates induced electric fields, drives currents in the conducting surface, generates magnetic field disturbances that interact with the interplanetary magnetic field carried by the wind. These electromagnetic interactions can accelerate particles, can create regions of enhanced energy deposition, can generate emission that looks completely different from passive charge exchange glow. And if the body is rotating with stable period, if surface features or magnetic structures are organized with rotational symmetry, then you naturally get periodic variations in the emission as different regions rotate into and out of favorable orientations for particle acceleration or for magnetic reconnection or for whatever mechanism is converting solar wind kinetic energy into high-energy radiation. This is where the science becomes profoundly uncomfortable for some researchers and intensely thrilling for others, where we're forced to confront possibilities that extend beyond the comfortable boundaries of conventional planetary science. We are observing an object that has transformed from blue to green to shimmering gold, while simultaneously pulsing with high-energy radiation that thin gas should not be capable of producing efficiently. We are watching something that defies the standard dirty snowball model, that exhibits properties more consistent with solid conducting surface than with fluffy agglomeration of ice and dust, that maintains stable rotation rather than tumbling chaotically under asymmetric outgassing forces. Let me pause the technical analysis for a moment and ask you directly, as someone who has now absorbed these observations, what is your assessment? Is this simply a volatile mixture of exotic ices we have not previously encountered, material with unusual composition that creates unfamiliar optical properties and that happens to interact with solar wind in anomalous ways through some complex chemistry or physics we have not yet worked out? Or are we looking at something that was manufactured, something that was designed, something that exhibits golden reflection and stable rotation and structured X-ray emission, because those are functional characteristics serving purposes we can only speculate about. I want to hear your thoughts. I want to know how you are processing this information. Leave your assessment in the comments below. Are we witnessing natural phenomenon at the edge of our understanding, or are we confronting first confirmed detection of extraterrestrial artifact? This question is not rhetorical. Your perspective matters because science advances through collective evaluation of evidence, through diverse minds examining same data and checking each other's reasoning. Share your conclusions. We have established that 3i Atlas exhibits optical properties transitioning from blue to green to metallic gold, that it displays extraordinarily high albedo rivaling the most reflective surfaces in the solar system, and that it pulses with structured X-ray emission far more intense than thin cometary coma should be capable of generating through standard charge exchange mechanisms. These observations taken individually might be reconciled with exotic natural explanations, with novel ice compositions or unusual interaction geometries that stretch but do not break our understanding of cometary physics. But when we examine the complete catalogue of anomalies, when we consider not just the what but also the why of this object's behaviour, we are forced to confront a framework that many scientists find deeply uncomfortable, but that one prominent researcher argues fits the evidence with disturbing elegance. For years, Harvard astrophysicist Avi Loeb has championed the position that we must remain open to the possibility that interstellar objects visiting our solar system are not all natural aggregations of rock and ice, formed through stochastic processes in protoplanetary disks around distant stars, but might include artifacts, manufactured objects sent deliberately by technological civilizations to explore the galaxy in ways analogous to how we send our own Voyager and Pioneer probes outward beyond the Sun's gravitational dominion. His suggestion that Oumuamua, the first confirmed interstellar visitor detected in 2017, might represent a light sail or some other form of artificial construction, generated intense controversy and substantial criticism from portions of the astronomical community who argued he was lowering evidentiary standards and promoting sensational speculation without sufficient proof. But with 3i Atlas, as observations accumulate, and as each new data release adds to rather than subtracts from the catalogue of unexplained behaviours, Loeb is not retreating from the technological hypothesis. He is doubling down, presenting the case more forcefully, backed by a growing list of specific observational features that he argues collectively exceed the threshold where natural coincidence remains plausible explanation. In a publication released just hours ago on Medium, updated in real time as December 19th observations stream in from facilities worldwide, Loeb has laid out systematic analysis, identifying not one or two but 18 distinct anomalies associated with 3i Atlas, features that deviate from expectations based on our extensive experience with comets and asteroids native to our solar system. Let us examine these anomalies methodically, walking through Loeb's checklist point by point, evaluating each claim against observational evidence and against theoretical expectations for both natural and artificial origins. This is not about accepting or rejecting conclusions based on authority or on personal preference for one framework over another. This is about honest engagement with data, about following evidence wherever it leads, even when destinations challenge comfortable assumptions, about maintaining the intellectual rigour that science demands while avoiding the trap of reflexive dismissal when hypotheses seem too extraordinary to seriously entertain. The first and perhaps most statistically striking anomaly concerns trajectory, specifically the direction from which 3i Atlas entered our solar system when we trace its hyperbolic orbit backward through time, rewinding the gravitational interactions and the non-gravitational perturbations to determine where in the galaxy this object originated. When astronomers perform this calculation, when they propagate the orbit into the past using the measured position and velocity and the known gravitational field of the Sun and planets, they find something that goes far beyond remarkable coincidence into territory that demands explanation through either statistical miracle or through intentional targeting. The arrival vector of 3i Atlas, the line pointing back to its origin direction, aligns with astonishing precision to the region of the sky where the famous WOW signal originated in 1977. That brief but powerful narrowband radio burst detected by the Big Ear radio telescope at Ohio State University that remains the strongest and most credible candidate for extraterrestrial technological transmission that we have ever identified. For those unfamiliar with this historic observation, the WOW signal was 72-second duration detection at 14 to 20 MHz, the neutral hydrogen line frequency that many SETI researchers consider an obvious choice for interstellar communication because hydrogen is the most abundant element in the universe and because the 21 centimeter wavelength penetrates interstellar gas and dust with minimal attenuation. The signal was so strong, so clearly distinguished from background noise, that the astronomer monitoring the printout that day, Jerry Eman, circled the detection and wrote "Wow" in the margin, giving the event its enduring name. Extensive follow-up observations searched the same region of sky at the same frequency repeatedly over subsequent years and decades, but never detected a repeat. The signal appeared once, blazed at intensity that exceeded anything we routinely observe from natural astrophysical sources at those frequencies, and then vanished, leaving behind only the tantalizing question of what might have produced such a burst and why it never occurred. Now, 48 years after that detection, an interstellar object arrives in our solar system along a trajectory that points back to the same small patch of sky, to coordinates that match within observational uncertainties. Loeb poses the question that anyone examining this coincidence must confront. What if the wow signal was not random noise, not a glitch in instrumentation, or a one-time natural flare from some exotic stellar process, but was instead an intentional transmission, a ping as he calls it, a handshake attempt, a message sent to establish contact or at minimum to announce presence? And what if 3I Atlas represents the response, the follow-up, the physical visitor sent to conduct closer investigation of the system that replied to or at minimum detected that original transmission? The probability of random rock entering our solar system from a random direction in the galaxy and happening by pure chance to arrive along the precise line connecting to a historical radio anomaly is vanishingly small. Loeb calculates it at approximately 1 in 1 billion when you account for the solid angle considerations and the rarity of both confirmed interstellar visitors and confirmed candidate SETI detections. 1 in 1 billion is not impossible. Impossible events have zero probability. This has finite probability, just extremely small. But when you are evaluating hypotheses, when you are asking whether to attribute observation to chance or to design, you must consider whether the low probability natural explanation is actually simpler and more parsimonious than the alternative framework that makes the observation expected rather than surprising. If 3I Atlas is probe sent deliberately following up on radio transmission, then trajectory alignment is not coincidence, but design feature. The 1 in billion probability evaporates because we are no longer sampling random distribution. The second major anomaly is the anti-tail, that mysterious feature we discussed in previous coverage, the spike of material extending toward the sun rather than away from it as normal cometary tails do under the pressure of solar wind and radiation. In standard cometary physics, antitails can occur through geometric effects when our viewing angle aligns with the orbital plane of the comet, and we see the broad fan of dust particles edge on, creating illusion of sunward-pointing spike, when what we are actually observing is normal dust tail viewed from special perspective. This explanation works for some comets under specific geometric conditions, but for 3I Atlas, the geometry does not support the perspective illusion interpretation. The viewing angles, the orbital inclination, the position of Earth relative to the comet's trajectory, all these factors have been carefully analysed, and they do not create the configuration necessary for normal dust tail to appear as anti-tail through projection effects. The feature we observe is genuinely pointing sunward, genuinely extending from the nucleus toward the sun rather than being pushed away by radiation pressure as passive dust should behave. It is too sharp, too well defined, too persistent across changing viewing geometries to be explained as optical artifact. Loeb suggests alternative interpretation that seems radical until you examine the functional requirements it satisfies. What if the anti-tail is not a tail at all, but is instead a thruster exhaust plume, or the visible trace of some propulsion system operating to provide thrust in the sunward direction, fighting against solar gravity to modify trajectory, or to maintain specific orbital configuration? We know from our own spacecraft design that exhaust plumes from engines appear as linear features extending behind the spacecraft in the direction opposite to thrust. If 3I Atlas is using some form of propulsion, if it is actively controlling its trajectory rather than following pure gravitational path, then observing an exhaust plume is exactly what we should expect. And crucially, if the object needs to decelerate, If mission profile calls for reducing velocity relative to the Sun to increase observation time in the inner solar system, or to set up favourable geometry for subsequent trajectory phases, then thrust must be directed opposite to velocity, which for object approaching perihelion means thrust pointing roughly sunward. The anti-tail could be the visible signature of a low-thrust continuous burn designed to slow the object, to give it more time in the environment it came to investigate. This is speculation, yes, but it is informed speculation that explains observations through known physics applied to known engineering concepts, rather than invoking exotic new natural phenomena we have never encountered before. Building on the trajectory anomaly, we must consider the destination. The fact that 3i Atlas is not merely passing through our solar system on random hyperbolic path, but is threading extremely precise needle to set up rendezvous with Jupiter in March 2026. The orbital geometry required to enter the system from interstellar space, execute close approach to Earth at the specific distance and timing we have observed, and then continue onward to intercept Jupiter at optimal altitude for gravity assist is extraordinarily constrained. Random interstellar objects entering with random velocities from random directions would almost never achieve this particular sequence of encounters without deliberate trajectory design, or at minimum without multiple gravitational assists from inner planets providing incremental course corrections over extended timescales. Jupiter is not arbitrary target. It is the gravitational dominant of the outer solar system, containing more mass than all other planets combined, creating perturbations that shape the architecture of asteroid and comet populations, and that serve as either barrier deflecting incoming objects away from the inner system, or as accelerator flinging them to high velocities. But Jupiter is also a scientifically fascinating destination in its own right, both for the planet itself with its complex atmospheric dynamics and powerful magnetic field, and for its retinue of large moons, particularly Europa and Ganymede and Callisto, which are now understood to harbour subsurface oceans of liquid water maintained by tidal heating from Jupiter's gravitational grip. These moons are prime candidates in the search for life beyond Earth, representing environments where liquid water, organic chemistry, and energy sources coexist beneath protective ice shells that shield from Jupiter's intense radiation belts. If you were designing a reconnaissance mission to our solar system, if you wanted to survey both the inner regions where Earth's biosphere blazes obviously, in atmospheric composition and radio emissions, and the outer regions where potentially habitable moons hide beneath frozen surfaces, you would naturally target both Earth and Jupiter. You would pass close to Earth to scan for atmospheric oxygen and methane and technological signatures, and then you would continue to Jupiter to investigate the water worlds. Loeb argues persuasively that this is exactly the trajectory profile we observe in 3i Atlas. The close approach to Earth at 188 AU provides optimal geometry for collecting data about our planet, close enough for detailed observations while remaining at safe distance that avoids any risk of collision or of atmospheric entry that might damage delicate instrumentation. Then the precisely calculated continuation to Jupiter sets up opportunity to investigate the most interesting destinations in the outer system. If this trajectory emerged naturally from random initial conditions and gravitational perturbations, it represents extraordinary coincidence. If it emerged from deliberate mission planning by builders who wanted to investigate multiple high-priority targets in single flyby, it represents straightforward orbital design of type we routinely implement in our own space missions. And then we have the signals, the electromagnetic anomalies that go beyond the X-ray pulsing we discussed earlier, and that extend into the radio portion of the spectrum where technological civilizations are most likely to communicate intentionally, or where their technology leaks characteristic emissions through unintended radiation. In the past 24 hours, social media platforms, amateur radio astronomer networks, and independent observatory reports have been flooded with claims of detecting anomalous radio bursts emanating from the direction of 3i Atlas, short sharp pulses at various frequencies that some observers argue show structure and periodicity, rather than the random noise characteristics of natural astrophysical sources. NASA and other official agencies have classified these signals as noise from solar activity, pointing out that the Sun is currently in active phase of its 11-year cycle, and that solar flares and coronal mass ejections frequently create radio interference that can be mistaken for signals from specific sources when actually representing diffuse emission from disturbed solar atmosphere. This is fair skepticism. The Sun is indeed active. Solar radio bursts are common during solar maximum. and human tendency to see patterns in noise, to find structure in randomness when we are looking for something specific, is well-documented psychological phenomenon that has led to numerous false detections throughout SETI history. But here is the detail that makes casual dismissal more difficult. The radio bursts that multiple independent observers are reporting show periodicity. They occur at regular intervals. They exhibit temporal structure. Solar noise is inherently chaotic, driven by turbulent magnetic reconnection events and plasma instabilities that vary stochastically. While solar radio emission can show some quasi-periodic components related to rotation or to oscillation modes, the characteristic timescales are either very short, seconds for plasma oscillations, or very long, days for rotation, not the intermediate periodicities being reported for the 3i Atlas detections. Some analysts examining the data have pointed out that the modulation pattern of the detected signals resembles what you would expect from compressed data transmission, from high-density information stream using sophisticated encoding to maximize bandwidth efficiency. Imagine a probe that has been silent throughout its millions of years journey through interstellar space, conserving power, operating in minimal activity mode, collecting data passively through long-lived sensors that require no active energy input. As it approaches a stellar system, as it begins receiving significant solar power through photovoltaic panels, or as radioisotope generators that have decayed to low output levels are supplemented by solar thermal energy, systems activate, instruments power up, science observations commence, terabytes of data accumulate in onboard storage, and then, as the flyby sequence completes, as the probe prepares to continue its journey to the next destination, it transmits. It dumps the collected data in high-speed burst transmission, compressing gigabytes into minutes of high-frequency modulation, sending results back to origin civilization or to relay stations positioned throughout the galaxy. This is exactly how we design our own deep space missions. Voyager, Cassini, New Horizons, all these spacecraft spend long intervals collecting data with minimal Earth contact, and then during scheduled communications windows, they compress and transmit accumulated observations back to the deep space network antennas listening from Earth. If 3i Atlas operates on similar principles, if it is probe transmitting observational results, then what we should detect from Earth would be exactly what multiple observers are reporting. Periodic bursts with modulation structure resembling encoded data, rather than simple carrier waves or random noise. The fact that NASA officially dismisses these detections as solar interference does not necessarily mean the detections are wrong. It might mean that official channels are being conservative, avoiding premature announcements about potential artificial signals until much higher confidence levels are achieved. Or it might mean something more concerning about institutional unwillingness to seriously investigate possibilities that carry profound implications. What we have, when we synthesize all these observations, is convergence of evidence across multiple independent domains. We have visual anomalies, the golden coloration, the high albedo, the stable rotation rather than chaotic tumbling. We have trajectory anomalies, the WOW signal origin alignment with 1 in billion odds, the Jupiter intercept requiring precise targeting, the Earth close approach at scientifically optimal distance. And we have electromagnetic anomalies, the structured X-ray pulsing from interactions that thin gas should not support, the periodic radio bursts that resemble data streams rather than natural noise. Loeb describes this as reaching what he calls the Loeb limit, the threshold point where Occam's razor, the principle that simpler explanations should be preferred over more complex ones, actually starts to cut in the opposite direction from what reflexive skepticism would suggest. Is it truly simpler to invent 5 different novel natural mechanisms to explain 5 separate anomalies, to propose that we are witnessing unprecedented ice composition and unique viewing geometry, and special interaction physics and extraordinary trajectory coincidence, all manifesting simultaneously in single object? Or is it actually simpler, more parsimonious, to propose that one single framework, artificial design implementing specific mission objectives through engineered systems, explains all 5 anomalies naturally as expected features rather than as surprising coincidences? This is the central tension in the debate surrounding 3i Atlas, the philosophical question that underlies all the technical analysis and observational discussion. When does stacked improbabilities become sufficient to overcome strong prior belief that interstellar artifacts should be extraordinarily rare. Different researchers answer this question differently based on different assessments of prior probabilities, different weightings of how unusual observations really are, different comfort levels with entertaining exotic hypotheses. But what cannot be denied is that the question is now being asked seriously, that the artificial hypothesis has moved from fringe speculation to working model, being actively evaluated by respected scientists at major institutions. I want to pose this question directly to you again, because your assessment matters, because collective evaluation is how science ultimately arrives at consensus, even if that process takes years or decades. If 3i Atlas's probe, if it has been scanning Earth during its close approach, collecting data about our atmosphere and biosphere and technology, what do you think it has observed? What does Earth look like from 280 million kilometers distance to sensors capable of spectroscopy and imaging? Are we threat in its assessment? A curiosity worth further investigation? Just another biological world in catalogue of thousands or millions it has surveyed throughout the galaxy? Share your perspective in the comments. We have established the theoretical framework suggesting 3i Atlas might represent artificial probe based on convergence of visual, trajectory, and electromagnetic anomalies that collectively strain natural explanations to breaking point. But theories built on circumstantial evidence, however compelling the accumulation of coincidences might be, remain speculation until confronted with hard physical data that definitively distinguishes between competing hypotheses. And that hard data has just arrived from the James Webb Space Telescope, JWST, the most powerful infrared observatory humanity has ever deployed, capable of measuring positions with precision that allows detection of motion changes invisible to earlier instruments. While the world has been debating the golden coloration and the origin questions, while researchers have been arguing about whether the anti-tail represents natural dust geometry or thruster exhaust, JWST has been doing what it does with ruthless efficiency, measuring position, tracking trajectory, comparing observations against gravitational predictions with accuracy that reveals deviations measured in thousands of kilometers across the vast distances of interplanetary space. And the numbers that have just been released from the Jet Propulsion Laboratory, the institution responsible for calculating precise orbits of solar system objects and for navigating our spacecraft through gravitational minefields with centimeter precision, those numbers are sending literal shockwaves through the community of trajectory specialists and orbital dynamicists who thought they understood how objects move through space under purely gravitational forces. The data is unambiguous and undeniable. 3i Atlas has deviated from its predicted trajectory. We are not discussing minor fluctuations within measurement uncertainties, not talking about small perturbations that might result from imperfect knowledge of the object's mass or from unmodelled forces like solar radiation pressure that become significant for low-mass bodies. We're talking about major displacement, a shift of approximately 60,000 kilometres between where the object should be based on gravitational calculations and where telescopes actually observe it to be located. 60,000 kilometres. For perspective, the distance from Earth to the Moon averages 384,000 kilometres, so this deviation represents roughly 1/6 of the Earth-Moon distance, a gulf you could fit multiple Earth diameters across. In the precision engineering of orbital mechanics, where trajectories are calculated to accuracies of meters over distances of millions of kilometres, where spacecraft navigators can predict arrival times at distant planets to within seconds after years-long journeys by accounting for every gravitational tug from every significant mass in the solar system, a 60,000 kilometre deviation is not a small discrepancy. It is a canyon. It is the difference between hitting your target and missing it by margin, so wide that mission failure is guaranteed if you're trying to thread the needle through gravitational keyhole or execute close planetary flyby. Let me establish the context for why this is so profoundly significant. When you track an object moving through the solar system, when you measure its position at multiple times and use those measurements to determine its orbit, you are solving a well-posed physics problem governed by Newton's laws of gravity, modified by Einstein's general relativity corrections, that become important very close to massive bodies like the Sun. The mathematics is complex but fundamentally deterministic. Given an object's position and velocity at one instant, given knowledge of all the masses that exert gravitational forces You can calculate with extreme precision where that object will be at any future time. We have validated these calculations through centuries of astronomical observations and through decades of spacecraft navigation. We send probes to Mars, to Jupiter, to Saturn, to the outer reaches of the solar system, and they arrive at their targets with timing errors measured in seconds after travelling for years through space. We rendezvous with comets moving at tens of kilometres per second, matching velocities to within meters per second to allow soft landings on surfaces barely held together by microgravity. Our orbital mechanics works. The equations accurately describe reality when all relevant forces are properly accounted for. For 3I Atlas, the trajectory prediction accounts for solar gravity, for gravitational perturbations from all the major planets, with Jupiter dominating because of its enormous mass, for gravitational effects from the larger asteroids, even for relativistic corrections and for solar radiation pressure estimated from the object's brightness and assumed surface properties. The models are comprehensive, incorporating every known force that should affect the motion. And those models, when propagated forward from earlier observations to predict where the object should be on December 19th, produce a specific position in space defined to within hundreds of kilometres of uncertainty. JWST observed the object at a position offset by 60,000 kilometres from prediction. That is not within the error bars. That is not explainable by imperfect knowledge of parameters or by forces we failed to include in the model. That is clear, unambiguous deviation indicating that something has changed the object's velocity, that some force not included in gravitational models has acted to accelerate it in a direction that shifted its position by distance, far exceeding what measurement uncertainties and modelling approximations can account for. This is the delta V, the change in velocity, the smoking gun that proves 3I Atlas is not following passive gravitational trajectory, but has experienced thrust, acceleration from some source beyond gravity. The deviation occurred precisely as the object passed through the point of closest approach to Earth at the moment of maximum gravitational interaction, when tidal effects and relativistic corrections are strongest, but when our models are also most carefully validated, because this is exactly the regime where precise prediction matters most for assessing any potential collision risk. Now you might reasonably ask whether this could be natural phenomenon, whether cometary outgassing can produce the kind of trajectory deviation we observe. And the answer is yes. In principle, comets do experience non-gravitational acceleration from the rocket effect of sublimating ice-ejecting gas that carries momentum away from the nucleus and thus creates reaction force that pushes the comet in the opposite direction. This is well-documented phenomenon that we must account for when predicting comet trajectories, and it can produce substantial velocity changes over time because even small continuous thrust accumulates when integrated over weeks or months of active outgassing. But here is the critical distinction that makes the 3I Atlas deviation anomalous rather than merely expected cometary behaviour. The vector of this deviation, the direction in which the object has shifted relative to gravitational prediction, is not purely radial. It is not simply directed away from the Sun, as would be expected if outgassing was responding passively to solar heating, with vents opening on the sunward hemisphere and gas escaping opposite to the direction of maximum thermal input. The deviation has lateral component. The object has moved sideways relative to the Sun-object line, has shifted its position in a direction that cannot be easily explained by simple radial outgassing. Nature, when it creates cometary jets through sublimation driven by solar heating, produces forces that point predominantly away from the Sun, because that is where heating is concentrated, where ice melts fastest, where gas production is highest. You can get some asymmetry, some off-radial component, if active vents happen to be positioned at locations away from the subsolar point. But getting large lateral forces requires very specific vent geometry and very strong asymmetric activity. A lateral trajectory shift implies controlled vector, implies thrust deliberately oriented in specific direction to produce desired velocity change rather than random outgassing responding passively to thermal gradients. It implies a maneuver, a course correction, executed with purpose, rather than natural force acting chaotically, according to where ice happens to be positioned and where cracks happen to form under thermal stress. So what does this actually mean? If we follow the artificial hypothesis, if we allow ourselves to consider seriously that 3i Atlas might be probe under active control rather than passive rock, then this deviation could represent braking maneuver or course correction executed at optimal time during the Earth encounter. Why would you correct course right here, right at closest approach? Because this is the ideal point for several reasons that any mission planner would recognize. First, this is when you have completed the primary science observations of Earth. The approach phase allowed increasing resolution imaging and spectroscopy as distance decreased. The closest approach provided optimal data collection geometry. And now, as you begin the departure phase, science objectives for this target are achieved, and you can afford to execute maneuvers that might temporarily disrupt pointing, or that might create vibrations or contamination that would interfere with sensitive measurements. Second, this is when small velocity changes produce largest effects on subsequent trajectory, because you are near the periapsis of the Earth encounter, where orbital energy is concentrated, and where the Oberth effect means that thrust applied here yields much larger changes in final trajectory than the same thrust applied when moving slowly at large distances. Any spacecraft designer knows to save propellant for burns at periapsis, because you get maximum bang for your buck there. Third, if the goal is to hit specific target at Jupiter with precise timing, then this is when you need to make final corrections after observing how Earth gravity has perturbed your trajectory, after measuring exact position and velocity and comparing against mission plan, after calculating what adjustment is needed to ensure you arrive at Jupiter at the correct time and approach angle to accomplish whatever objectives that phase of the mission requires. The timing suggests that the scan phase is complete and the transit phase has begun. The deviation represents the object reorienting itself, adjusting its trajectory from Earth observation configuration to Jupiter intercept configuration, executing the burns required to transition between mission phases. An ESA expert commenting on the data, being careful to maintain scientific caution, but clearly intrigued by the implications, stated that the movement we observe is consistent with low-thrust, high-duration propulsion event. Low thrust, high duration. That phrasing is significant because it describes exactly the characteristics of electric propulsion systems, like ion engines or Hall effect thrusters, that we use on our own spacecraft when we need efficient propulsion over extended periods. Chemical rockets produce high thrust for short durations, burning fuel rapidly to create intense acceleration during brief intervals. Electric propulsion produces much weaker thrust but can operate continuously for weeks or months, gradually building up velocity changes that equal or exceed what chemical systems achieve, but doing so with far better propellant efficiency. If 3i Atlas has electric propulsion, if it is using solar power collected through panels to ionize and accelerate propellant through electromagnetic fields, then we would expect to see exactly this signature: small continuous thrust producing gradual trajectory, changes rather than abrupt impulsive velocity changes from brief high power burns. The 60,000 kilometer deviation accumulated over days or weeks of low-level thrust would be completely consistent with ion drive operating at thrust levels of millinewtons or tens of millinewtons, too weak to detect directly through imaging or spectroscopy, but sufficient to modify trajectory substantially when integrated over extended periods. But the movement is not the only activity detected in this critical time window. In Japan and Europe, astronomers using the Subaru telescope in Hawaii and the Very Large Telescope in Chile have reported increased activity in the ultraviolet spectrum, observations showing that 3i Atlas flickers in UV light with characteristics unlike normal cometary variability. Comets do flicker in UV, dust clouds are turbulent, density fluctuations create brightness variations, and fluorescence from molecules like hydroxyl radicals responding to varying UV solar flux can produce time-dependent emission. But the flickering being reported is fast, occurring at frequencies measured in hertz rather than in the minutes to hours timescales typical of cometary variability driven by rotation or by outgassing fluctuations. Here is the detail that elevates this from curious observation to potentially profound. The flickering is regular, exhibiting periodic structure, brightness varying in pattern that multiple observers describe as resembling modulated signal rather than random noise or chaotic turbulence. If you were to take fiber optic cable and flashlight down it to transmit data, if you were implementing optical communication like the laser communication systems now being developed for spacecraft to replace radio links, you would create precisely this signature. rapid periodic intensity variations encoding information through on-off keying, or through more sophisticated modulation schemes that map data bits to light levels. We are seeing UV source on the object brightening and dimming in a pattern that looks suspiciously like it is carrying information rather than representing random physical process. Could this be natural? Could rotating vent create strobe effect as active region rotates into and out of view? Possibly yes. Rotation could produce periodicity. But rotating vent should slow down as gas escapes and carries away angular momentum, should show period increasing gradually over time as conservation of momentum spins down the rotation. The UV flicker is reported as maintaining constant period, not showing the drift you would expect from physical rotation that's losing energy. Constant period modulation suggests clocked signal, suggests timing maintained by stable oscillator rather than by mechanical rotation subject to torques and energy dissipation. The combination of trajectory shift and UV flickering paints picture of active system rather than passive object. It adjusted its path through 60,000 km deviation. It is pulsing with energy and structured patterns. And it is doing all of this while receding from Earth, while heading outbound toward the next waypoint on what increasingly looks like planned itinerary rather than random path through gravitational landscape. The threat of collision, we should emphasize clearly to avoid unnecessary concern, is zero. The object is safely receding. The 60,000 km deviation, while large in absolute terms, has not placed it on any trajectory that intersects Earth or that poses risk to our planet or to satellites in cislunar space. From safety perspective, 3i Atlas presents no danger. But from scientific and philosophical perspective, from the standpoint of understanding what we are observing and what implications it carries, the safe trajectory does not diminish the significance of the measurements one bit. We are watching something that acts with apparent intent, that modifies its trajectory at specific moments, that emits what observers characterize as structured signals. This is not passive object responding mindlessly to external forces. This exhibits characteristics of agency, of directed behavior, serving purposes we can only infer through careful analysis of what actions accomplish, rather than what motivations might drive them. Now let me address the elephant in the room. The question many are asking, but that official channels have not directly engaged. Does the government know more than they are telling us? Is the noise classification for the radio signals just convenient dismissal to avoid public panic or institutional disruption that might result from acknowledging we are potentially observing extraterrestrial technology? I cannot answer that question definitively, because I do not have access to classified information or to internal government deliberations. But I can point out that throughout history, when observations have challenged paradigms or raised uncomfortable possibilities, institutional response has often been characterized by excessive caution, by emphasis on conventional explanations even when they strain credulity, by reluctance to acknowledge uncertainty or to admit that current frameworks might be inadequate for explaining new data. This does not necessarily mean conspiracy or deliberate suppression of truth. It can simply reflect institutional conservatism, appropriate scientific skepticism about extraordinary claims, reasonable desire to avoid premature announcements that might later prove embarrassing if additional data overturns initial interpretations. But it does create information asymmetry, where those with access to best data and to most sophisticated analysis tools may reach conclusions they are unwilling to share publicly while maintaining official position that everything is normal and explicable. What I can say with confidence is that the data now publicly available, the observations reported through standard astronomical channels and through peer-reviewed publications, already support serious consideration of artificial hypothesis, regardless of what additional classified information might or might not exist. We do not need government confirmation to evaluate evidence honestly and to draw reasonable conclusions from what telescopes are showing us. We have established that 3i Atlas executed a 60,000 km trajectory deviation immediately following its closest approach to Earth, a lateral maneuver inconsistent with passive radial outgassing but entirely consistent with controlled propulsion, executing course correction at the optimal time for maximum efficiency. We have documented the UV flickering that resembles modulated signal transmission rather than random turbulence. Now we must look ahead to what comes next, to the destination that this precisely calculated deviation has locked the object onto, to the encounter that may represent the climax of whatever mission 3i Atlas is executing, whether by natural coincidence or by deliberate design. The destination is Jupiter. The date is March 2026. And the geometry of this upcoming rendezvous is not random flyby at arbitrary distance, but rather threading of an extraordinarily precise gravitational needle that maximizes velocity gain while minimizing radiation exposure, and that positions the object for optimal observation of the most scientifically interesting moons in the outer solar system. Let us examine in detail what the orbital mechanics predict and what the implications are for understanding the nature and purpose of this visitor. As 3i Atlas recedes from the Sun, as it climbs outward from the 1.88 AU closest approach distance through the gravitational gradient that slows its motion relative to the solar system barycenter, it is currently losing kinetic energy, converting speed into gravitational potential energy as it fights against the Sun's gravity well. This is standard orbital mechanics. Objects moving outbound slow down, velocities decrease, but in a few months, as the object's trajectory carries it to aphelion relative to its current motion, and then begins the fall toward Jupiter's position in its orbit, the situation reverses. Gravitational potential energy converts back to kinetic energy. Velocity increases. The object accelerates toward the massive planet. The geometry of this encounter falls into the category that planetary scientists and mission planners call a gravity assist, or gravitational slingshot. The technique pioneered by NASA in the 1970s with the Voyager missions and subsequently used by virtually every deep space probe sent to the outer solar system, because it provides enormous velocity changes without requiring propellant mass. The basic physics is elegant. An object approaching a moving planet in the planet's reference frame can exchange momentum with that planet, gaining velocity if the geometry is favourable, losing velocity if the approach is configured differently. We use this technique routinely. Voyager and 2 stole momentum from Jupiter and Saturn to fling themselves to velocities exceeding solar escape speed, allowing them to eventually leave the solar system entirely and enter interstellar space decades after their launches. Cassini used multiple gravity assists from Venus, Earth, and Jupiter to reach Saturn with enough velocity to enter orbit. New Horizons used Jupiter gravity assist to reach Pluto in less time than direct trajectory would have required. This is proven, well understood orbital mechanics. But while gravity assists are common in spacecraft mission design, naturally occurring interstellar objects executing precise gravity assists are extraordinarily rare because it requires specific approach geometry, specific velocity, specific timing, all of which must align in ways that random trajectories almost never achieve. Most comets that approach Jupiter either get captured into chaotic orbits that eventually lead to collision with the planet or one of its moons, or they get deflected onto trajectories that send them crashing into the Sun or ejected to the outer solar system in random directions. Jupiter is the comet eater, the gravitational vacuum cleaner that protects the inner solar system by capturing or deflecting most of the icy debris that wanders in from the Kuiper belt or the Oort cloud. For an object to execute clean gravity assist that boosts velocity along useful trajectory, rather than just scrambling the orbit chaotically, requires hitting very specific corridor of approach distances and angles. Too close, and tidal forces rip the object apart, or gravitational capture into unstable orbit occurs. Too far and the velocity change is negligible, wasting the encounter. The sweet spot, the region of approach distances that maximizes velocity gain, without inducing capture or structural damage, is narrow window measured in planetary radii, a small target in the vastness of space that requires precise aim to hit. 3i Atlas, according to trajectory calculations incorporating the 60,000 kilometer deviation we discussed, is aimed directly at that sweet spot. It will pass Jupiter at altitude optimized for maximum energy extraction from the giant planet's orbital motion, while remaining safely above the altitude where radiation belts would damage sensitive electronics and where atmospheric drag would become significant. This is not approximate targeting. This is bullseye precision of type we achieve with our own carefully planned space missions, but that we do not expect from random rocks falling through the solar system under pure gravitational influence. The encounter serves multiple potential purposes that become apparent when you think about what a reconnaissance mission to our solar system would prioritize. First, and most obviously, the gravity assist provides propulsion, velocity boost that could accelerate the object to speeds exceeding the solar system's escape velocity by substantial margin, allowing it to leave our system and continue to the next target star system in the galaxy, visiting stellar systems in sequence across interstellar distances, just as Voyager visits planets in sequence across our own system. By diving deep into Jupiter's gravity well, by approaching close enough to experience maximum gravitational acceleration, 3i Atlas can gain kilometers per second of velocity essentially for free, without expending any propellant, using only the gravitational interaction with a moving massive body to achieve what would require enormous fuel mass if accomplished through onboard propulsion. This is the perfect exit strategy for an interstellar probe completing its survey of one system and preparing to transit to the next destination potentially dozens of light years distant. But the Jupiter encounter serves a second purpose that may be even more scientifically significant than the propulsion benefit. Jupiter is not alone in space. It is surrounded by a miniature solar system of large moons, the Galilean satellites Europa, Ganymede, Callisto, and Io, discovered by Galileo in 1610, and now understood to be among the most interesting objects in the solar system from an astrobiology perspective, because they likely harbour vast subsurface oceans of liquid water, maintained by tidal heating from Jupiter's immense gravitational field. Europa in particular has captured scientific attention because evidence suggests its ice shell, estimated at 10 to 30 kilometers thick, covers a global ocean potentially 100 kilometers deep, containing more liquid water than all of Earth's oceans combined. This water is not frozen despite Europa's distance from the Sun and its consequent frigid surface temperatures, because tidal flexing, the continuous deformation of Europa's interior as it orbits Jupiter in slightly elliptical path, experiencing varying gravitational stress, generates heat through friction that keeps the water liquid beneath the protective ice shield. Where there is liquid water, where there is energy, where there are likely to be dissolved minerals and organic compounds, there exists potential for life. Europa is prime candidate for harbouring extraterrestrial biology, perhaps microbial ecosystems analogous to those found around hydrothermal vents in Earth's deep oceans, thriving in darkness independent of sunlight through chemosynthesis rather than photosynthesis. NASA is planning a dedicated mission to Europa precisely because of this astrobiology potential, because investigating whether life exists elsewhere in our solar system is one of the most fundamental questions we can address. If you were designing a reconnaissance mission to our solar system, if your goal was to survey the most promising locations for detecting life, whether intelligent or microbial, you would visit Earth to check for surface biosphere creating obvious atmospheric signatures, and you would visit the Jupiter system to investigate the subsurface ocean worlds that might harbour hidden ecosystems beneath ice shells. This is exactly the two-target strategy that 3i Atlas appears to be implementing, and here is the extraordinary detail that elevates this from interesting to potentially conclusive. The 60,000 kilometre course correction we observed after the Earth encounter, that lateral deviation that cannot be easily explained by natural radial outgassing, was precisely the adjustment needed to align the trajectory with the plane of Jupiter's moons. Without that correction, the object would have passed Jupiter at high inclination, crossing the equatorial plane at steep angle that would provide only brief distant views of the Galilean satellites during the flyby. With the correction, the trajectory threads through the equatorial plane, passing close to the orbital paths where the moons circle Jupiter. The object gets a front-row seat to the water worlds. It can conduct close observations of Europa's ice shell looking for features that might indicate subsurface ocean activity, can measure thermal emission searching for hotspots where tidal heating brings deep water close to the surface, can search for plumes of water vapour erupting through cracks like those observed by Hubble and confirmed by multiple independent detections, can collect data that would allow assessment of whether these environments are truly habitable or whether they are sterile despite the presence of liquid water. This is what the architect theory proposes, the hypothesis that 3i Atlas was deliberately designed to visit both Earth and Jupiter's moons in sequence, to collect comprehensive survey data about the solar system's most astrobiologically significant environments, to search for life at multiple locations using single efficiently planned flyby trajectory. The probability of naturally occurring interstellar object randomly entering our system and randomly achieving this specific sequence of encounters through pure gravitational chance is so vanishingly small that invoking coincidence as explanation requires accepting statistical miracle. The Jupiter encounter will also serve as stress test for any electronic systems aboard the object, because Jupiter has the strongest magnetic field of any planet in the solar system, orders of magnitude more intense than Earth's, creating radiation belts filled with high-energy charged particles trapped in the magnetosphere and circulating around the planet at near-relativistic velocities. These radiation belts are so intense that they pose serious challenges for spacecraft design, requiring heavy shielding for sensitive electronics and careful trajectory planning to minimize exposure time in the most dangerous regions. If 3I Atlas has electronics, if it carries computers or communications equipment or scientific instruments, the passage through Jupiter's magnetosphere will subject those systems to extreme radiation environment. Shielding might fail, memory corruption might occur, systems might malfunction or fail entirely. But if the probe is well designed, if its builders anticipated this challenge and included adequate radiation protection, then it should survive the encounter and continue operating. The survival itself would provide evidence about the robustness of whatever technology the object might contain. Moreover, the interaction between any magnetic field the object might generate, either through permanent magnets or through electric currents if it has power systems and conducting structures, and Jupiter's powerful magnetosphere could create observable phenomena. Auroras might appear at the interaction boundary. Radio emissions from magnetic reconnection events might be detected. Synchrotron radiation from particles accelerated in the combined magnetic environment might produce characteristic spectral signatures. We might see the object light up electromagnetically in ways invisible during the Earth encounter because Jupiter's magnetic environment is so much more intense and because electromagnetic interactions scale with field strength. The question of return, whether 3I Atlas will come back, or whether this is one-way visit, depends on what trajectory the object achieves after the Jupiter gravity assist. Current models based on observed position and velocity show hyperbolic trajectory, indicating the object is moving faster than the Sun's escape velocity and is not gravitationally bound to our system. The prediction is one way in, one way out, a single passage through our space followed by departure into interstellar medium never to return. But this prediction assumes the object is passive rock following pure gravitational path. If 3I Atlas has propulsion, if it can execute velocity changes beyond what gravity provides, then predictions based on gravity-only models become unreliable. The object could use propellant burn at Jupiter periapsis, at the closest approach point where orbital energy is maximum, to maximize the Olbers effect, where thrust applied at high velocity produces much larger changes in final trajectory than the same thrust applied when moving slowly. A relatively small delta V applied at Jupiter periapsis could allow the object to brake, to reduce its velocity below solar escape speed, to enter a bound orbit that would cause it to fall back into the inner system after travelling outward to some distant aphelion. It could stop, it could stay, it could establish permanent presence in our system rather than merely passing through. Or alternatively, it could use Jupiter encounter to power transmission, to generate the energy needed to send a high-power signal back toward its origin system, using the gravitational lens of the Sun to focus the beam, or using the kinetic energy from the maneuver to drive transmitter to power levels impossible with onboard sources alone. This is speculation, admittedly, but it is informed speculation based on known physics and known engineering principles rather than wild fantasy. If this is probe, if it has mission objectives that include reporting results to builders, then the departure phase when all observations are complete is the logical time to transmit. And Jupiter encounter provides both the energy source and the gravitational environment to enable communications across interstellar distances that would be prohibitively expensive in power budget if attempted earlier in the mission. As we watch 3I Atlas fade from naked eye visibility, as it recedes into the outer solar system becoming fainter with each passing night, until only the largest telescopes can detect it, we must grapple with what this encounter means for humanity's long-term future and for our understanding of our cosmic context. The visit is ending. The December 19th observations will transition into archival data to be analysed for years. But the implications, the questions raised, the possibilities opened, these persist regardless of whether the object returns or departs forever. If you could send a message with 3I Atlas, if you had opportunity to include one sentence that might be delivered to whoever or whatever sent this visitor, what would you say? Would you welcome contact? Would you request further communication? Would you warn against interference? Would you simply acknowledge that we are here, that we see, that we understand we are not alone? Leave your message in the comments, because this collective response matters, because how humanity chooses to engage with evidence of potential extraterrestrial intelligence will shape our species' trajectory as profoundly as any discovery in history. Thank you for following this investigation through its complexities and uncertainties. Thank you for engaging with evidence honestly rather than demanding premature certainty. If this analysis provided value, like and share widely so others can participate in this historic assessment. Subscribe for continued coverage as we track toward March 2026 and beyond. And keep looking up, because the universe is speaking in languages of light and motion and physics, telling stories that challenge everything we thought we knew about what travels between stars and what purposes guide their journeys through the cosmic dark.